All right. Yeah, okay. Now it is being live streamed, so we can now start. It has not been connected to YouTube. So good day, good morning, good evening. You're welcome to our paper reading group presentation. We are presenting on the paper StreamDiffusion, a pipeline level solution for real-time interactive generation. We are three presenters. I will be starting, and my name is Aminu Mohammed Chumesi from Ghana. Then Bushra Jabin will continue. Then Esther Wabumba will finalize for us. So kindly let's start. So what are we going to tackle in this paper, right? This paper, we are coming to look at the overview and related work. Then we will look at the method and structure. Then we look at the experiments and the results that are contained in the paper. So after we are done with the overview and related work, we move on to the method and the structure. That is what makes up the paper, all right? Then we'll finish it up with the experiments and the results. Then other things that we learned from the paper as to the pros and cons, the limitations, further areas of research, we also tackle those ones. Those ones are like opinion kind of things. So we'll look at those ones getting to the end of the presentation. So let's look at the overview, StreamDiffusion. So what is StreamDiffusion? Looking at this image or this slide, you can see that there are some prompts that have been given to a certain system, and it's generating a lot of images. And you see that it's very, very fast, all right? It's very, very fast. So this is what StreamDiffusion basically hopes to achieve, all right? So let's quickly get to it. So what is StreamDiffusion? Already, we have these models in machine learning. We already have these models called Stable Diffusion. Now, Stable Diffusion came on the scene some years ago, but with Stable Diffusion, even though we can generate images, but there was a problem because just like everything, we try to make things more perfect, more streamlined, and more a bit faster than it used to be. So with the normal Stable Diffusion, you realize that when you are prompting or you want it to generate images, it takes quite some time. When you download the Stable Diffusion package and you install it, you just enter your prompt, then you wait, you click on it, you wait for some time before the image will be generated. And a team sat down and were like, no, how can we make this process faster? Like even when we are typing your prompt, immediately it is being fed into the system. Then maybe based on your prompt, an image will start to be generated. Then as your prompt is being finalized, then the final image will also be generated based on it. We did not want to wait. We wanted something that is very fast. And these people came up with a term for it called StreamDiffusion, meaning that as you are typing, as you are working on the prompt, then the image is being generated in real time. So StreamDiffusion tries to solve the problem of real-time interactive generation in diffusion models, which diffusion models fails to achieve. Because with diffusion models, you have to enter your prompt, then give it to the model, then it will work on it for some seconds or for some minutes, depending on the capability or the resources that the system has before it gives you the output, which we are trying to eliminate. So as we know, with Stable Diffusion, the models are known for their slow speed in generating output. It takes quite some time before they generate their output, all right? And what also StreamDiffusion hopes to achieve is that it introduces a pipeline level solution, all right? We are introducing some sort of a low level pipeline. So it means that as you are working on your prompt, as you are working on the image you are giving to the system, even if you feed an image to the system and you are giving it a certain prompt, you want a certain modification, even when you type any single letter that you type, already the model will pick it up and start working on it to generate something similar to what you are prompting it to be. So that even by the time you finish typing, your image is ready, or what you want, the output that you want is ready based on the prompt that you give to the system. And how did they achieve this thing? They achieved it through some certain tools or technology that they implemented. And some of the tools are Stream Batch, Residual Classifier-Free Guidance, or RCFG, which is based on the CFG model, all right? And the input and output queue for parallelization. Then Stochastic Similarity Filter, SSF. Then you also have pre-computation. Then they also did some model acceleration with what tool? They use tiny autoencoder to do that. Let's get to it. So let's look at the method and the structure. So the tools that they use to achieve this fast generation of images, all right? StreamDiffusion is built on top of Stable Diffusion. So no two ways about that. It's not that it's a separate thing. No, StreamDiffusion is basically built on top of Stable Diffusion, but they have introduced a pipeline level of architecture that makes it possible that images are generated in real time, very interactive and very fast. And that pipeline level is what we are going to learn, the method and the structure, what they use for it, the tools that came together to make the pipeline, and how fast it is. Those are the things we are coming to look into it. So the first one, we have the stream batch strategy. And what does the stream batch strategy do? With normal stable diffusion models, you have to give it an input, all right, one at a time, all right? You have to give it an input one at a time. So it finishes with this input, generates the image, then it comes to the other one, then it finishes with generate an image. Then the people who came up with stream diffusion were like, no, that shouldn't be the case. Is there a way that we can make it in such that we can give it multiple inputs, then it will stream, it will put it in more like a batch production kind of thing. It's finished with it, then come to the effect with this. As this one is generating, if it breaks a bottleneck or it's finished, like it reaches a part that it's loading, then it switches to the other input, then it works on it. So that even if you give it 10 images, within some few minutes or seconds, the images will all be generated, unlike waiting for it in stable diffusion, whereby you have to give it one image, you have to wait for, let's say, about 30 seconds, 1 minute, or even more, depending on what you are generating, for the image to come. Then you give it another input, which is quite hectic. So we are looking at a way we can feed it with multiple inputs, and all of these inputs, outputs, be generated within minimal seconds or even minutes compared to stable diffusion. All right. So that's what the stream batch strategy is all about. Then they also implemented RCFG, all right? The RCFG is basically based on the CFG. The CFG is the Classifier-Free Guidance, right? They realized that with the existing CFG that is being used in stable diffusion, the system was a bit slow, and the one who is prompting the system had less control over it. So they had to introduce another algorithm, an algorithm on top of the CFG, and they call it Residual Classifier-Free Guidance, whereby this one, they have more control over it, over the algorithm, and they can control its refinement as to the final output of the image. So it's basically, this one is basically an algorithm they introduce into the pipeline to help with fine-tuning the output or the final image that will come. So there's an example image of something like this. So you see here, we have an input image, all right? This is without CFG. So it means that without CFG, this is how the image, if you give it to the model, this is how it will appear like, all right? Then with CFG, this is how it will also appear like. This one, we are prompting for white tiger. We gave it an image of a cat, all right? And we are prompting it for white tiger, that you should convert that image to a white tiger. Without CFG, this is how, if CFG is not part of the model, this is how it will appear like, or the algorithm is not present, this is how it will appear like. With CFG2, this is how it appears like. It's then looking here, you see that with our CFG, that's the residual one that it brought into the mix. If they have the self-negative, this is how the image is appearing like. And if you have the one-time negative, so you see like the one-time negative, it's much more refined than even the self-negative. So that is the impact of the RCFG in the whole pipeline, that algorithm, all right, is to help refine the images, make it better. So looking at this, even with CFG and looking at this, you see that this one is far better and resembles more a white tiger than this one, even with the CFG algorithm. So that's why this RCFG, they recomputed the calculation to bring in the residual one so that they use it to have more control and refinement over the end output. The same thing with this one, all right? So all of these images, when you look at it, this is the first one is with the image that you give to the model. Then if it's without CFG, how it's going to be outputted. If it is with CFG, and if it is the self-negative RCFG, how it will be like. Then if it is one-time negative, and the one-time negative is what they really hopped on to make it work. All right. Then let's come to the third tool that they use in the pipeline. We call it the input and output queue. So what is the input and output queue? Basically, what they did is that they wanted parallelization, all right? They don't want it in a way that one image will finish, even though we have given the input, whether images, whether text, we have given it as a stream or a batch to the system. So it is processing all at the system. We don't want delays. So what is the input and output queue? It basically paralyzes the whole thing, all right? So if there's anything that they need to do on it, all right, or specific operations like resizing, conversion, normalization are meticulously executed for input image handling, all right? So what the input queue basically does is that it takes some of the input that they've given to the system, even outside of the pipeline, then works on it, then brings it back into the pipeline to continue the process so that there will not be delays, there will not be bottlenecks, because you want the stable diffusion to perform at its fullest, the fastness of the stable diffusion is what we want. So the pipeline is what we are introducing, and we want to eliminate any bottleneck, anything that will delay the process. We want to take it off so that the system will be as fast as it can be. So that's why the input and output queue was introduced, just to make sure that if there are something that can delay in the pipeline, we take it outside of the pipeline, work on it, then bring it into the pipeline to continue the process so that other processes in the pipeline can flow smoothly and there will not be any bottleneck in the system. Then let's come to the SSF, that's the Stochastic Similarity Filter. And basically, the Stochastic Similarity Filter is basically to help the GPU or the resources that are being used to run the system, all right? And what does it do? It gates. It's basically like a smart gate. So when you give an input to the system and it feels like, oh, this input that I'm coming to give, they are all similar. It tells the CPU to, tell the GPU to cool down, all right? Don't spend so much resources on generating, because this one we have generated already. We don't need to spend so much resources on generating it again. Let's look at an example, all right? So looking at this example, for instance, all right, we are saying that the stochastic or the SSF reduces processing during video input by minimizing conversion operation. When there is little change, it's just like, let's say let me use Git, for example, all right? When you are sending something to Git, all right, Git does not store, if you are doing Git commit, Git does not store everything from scratch. If, let's say, you work on a file and you do the Git add and you stage it for Git and you commit it to Git, all right, when you make any changes to it, it's only the changes that will be recorded in the Git. They will not do everything from scratch again because they already have a record of it, all right? So this is exactly the same. Instead of doing if let's say you're giving me an image or you are prompting me for something, and that thing is just a minor change that you want to do to it, there's no need for me to generate the entire image again. I already have it. So I only need to do the 1 or 2 adjustments that you are prompting me to do, which Stable Diffusion fails to do, because Stable Diffusion will still do everything from scratch, further elongating the timeline that it takes to complete a certain input or a certain prompt. Then pre-computation, another tool that they have. So pre-computation is basically, pre means before and computation means to calculate, all right? So basically, before the system even starts running or the pipeline even starts running, if there are any computation that needs to be done, they do it even before the pipeline, the prompt is given to the prompt is sent into the pipeline, so that things that will delay, as I mentioned, we want to eliminate any bottleneck so that image generation is very fast and very interactive. So any computation that we need to do, we do it before even the pipeline starts to run, so that it will not result in any bottleneck in the entire system or in the entire pipeline, so that everything will flow smooth and within seconds you have your image generated for you in real time. Then the model acceleration with tiny autoencoder. So the tiny autoencoder for stable, that's the TAESD, tiny autoencoder for stable diffusion. So we wanted the model to also be very fast and high performing. What did the stable diffusion model? We wanted it to be very fast. What did we do? We introduced tensor RT in it, all right, to make it very fast, all right. Then we also introduced tiny autoencoder into it to accelerate the process of the model, so that if, let's say, with prompt, it normally takes an average of 10 seconds. This time around, once we have introduced some accelerators in it, it will take, let's say, 5 seconds or less. We want the thing to be very fast, because it's something that we want it to be very interactive within real time kind of thing. So there's an example of, there's a graph showing the model acceleration in tiny autoencoder. All right, there's a graph of it. So let's come to the live demo. Unfortunately, with the live demo, we have the source code, everything. We have some code there in Google Colab. But one thing we realized was that with this one, with the StreamDiffusion, it's best that you do it in your local, or you download the Docker file and you run it itself. Running it in Google Colab will not give you that fastness that you desire. But when you run it in Google Colab, it's basically like doing it in Stable Diffusion. You have to be running the prompt here and there. But unfortunately, with their live environment, it's not all laptops or all environment that can contain it. So most of us, we are not able to have these live environments because it uses a lot of GPU here and there, and we do not have the needed resources to do it. But still, without that, we still have some demos we can show you. So looking at this, all right. So when you download the Stable Diffusion package, StreamDiffusion package, when you download it, they have a Docker file that you can download as a container that contains everything that you need. And you need to have the GPUs and everything that you need to run it and everything. So when you download it, they have the input section and the output section. So when you look at it this way, you see that right now, the person who did the demonstration is trying to model something like a wave. And as they are trying to do their, this one is image input. So they are giving it some sort of like an image input, but they are drawing it, all right, or a drawing input. So they are drawing something similar to a wave. Then the model is trying to read and understand what they are doing, and it is generating this in real time. As they are doing it, then it's generating it in real time. As I said, we hope this thing to eliminate bottlenecks, unlike stable diffusion, whereby I will need to draw the image, give it to the model, wait seconds or even minutes before it generates. And at times it might not even be that accurate, depending. All right. It might not even be that accurate. All right. We have to wait minutes or even seconds for it to generate. This one, as we are giving the prompt here in the canvas, then it is using that and it is generating an instant feedback for us in real time, and it is very interactive. Let's look at another prompt. So with this one, you see our user has drawn a canvas of like the skyline, all right? And as he's moving the sun down, here in real time, our StreamDiffusion is anticipating everything, knowing that, okay, the person is trying to imitate like sundown or sunset. So it is doing the exact same thing for him or her. So this is in real time. As we are giving the input, then the output is happening in real time. There are no delays because we have eliminated the bottlenecks that stable diffusion normally presents, all right? And we have a pipeline that is very fast, that are free of bottlenecks to help you achieve that interactive and real-time thing that you need to get. There is also another image, all right? We are looking at a waterfall. So the prompt in the canvas is that the person is trying to draw a waterfall, and interactively, in real time, the stream diffusion pipeline has been set in a way that it's also trying to focus and give it an image as to what it is trying to do. So this one, if this is not what we are trying to draw, then immediately you can even just erase it or try to redraw it, or try to like do the drawing in a way that the stable diffusion will pick it up and know exactly what you are about. So this is an example, all right? This is a demo example of how the stable diffusion works. It's in real time. It's in real time. The best way you can use this stream diffusion is to have the package in your local system or hosted on a machine with a lot of GPU. Then you can test both out, all right? You can test both out. Then you really get to understand the power of it. There's also, this one, we look at the text-to-image prompt of it. We are looking at the text-to-image. So you see, we are prompting it, one girl, cat eyes, Ikijo, Mount Fuji. Then immediately, as we are giving the prompt, as I said, we have eliminated all the bottlenecks in the pipeline by implementing what? Stream batch strategy. We have implemented pre-computation. We have implemented SSF. We have implemented model acceleration with tiny encoder, all right? And other things that we have in the pipeline that actually helps us to have an interactive environment and live environment. As and when we are prompting, then everything is in it, all right? We have it in that way. So as you are prompting, then it is generating it in real time for you. You don't have to wait. Unlike the normal stable, the traditional stable diffusion, whereby you have to submit and wait for some seconds and even minutes. This one too, if you submit an image, this is an image-to-image submission. So if you submit an image, you can submit an image, all right? You can stream the image straight from your webcam or from a camera. And as you are prompting it, it will be generating the what you are prompting in real time, no delays. There's an image. This one is the person is streaming from their FaceTime camera, all right? So it's in real time. And as they are prompting how they want it to be transformed, it is being transformed for them. Then we come to the experiments and the results. And from this part onwards, I'll call Bushra to continue. So far, before Bushra starts, so far, we've looked into what the stream diffusion is, what it hopes to achieve. As we know that with stable diffusion, with the normal stable diffusion method, there's a lag in the pipeline, whereby when you give a prompt, it takes quite some time. It's not interactive. It's not real time. All right. And we see, whenever we are working on AI or machine learning, whatever, we need things to be practicable. All right. You want things that can be implemented in real working scenarios or real working environment. We don't want things in theory, or we don't want things that are slow and lagging. All right. So stream diffusion is to solve the problem where stable diffusion lacks by implementing a pipeline. In that pipeline, you have stream batch strategy there, whereby it processes your prompt in batches. All right. And it also has pre-computation, whereby any computation necessary for your prompt to work, it does it even before the prompt starts working, so that it goes through a very fast process. It has SSF, that is Stochastic Similarity Filter, whereby with that one, if you've given it a prompt and it has generated a certain output for you, if you want modification, it will not generate it again, like from scratch. It will just implement the only new feature that you are stating that you should implement. Then we have also accelerated the stable diffusion model with tiny encoder and other things here and there. All right. Then we also have other RCFG, all right, whereby we have used the one-time negative to make sure that we have more control and refinement over the final output or image or whatever we want the stream or the pipeline to give to us. All right. So Bushra, if you can kindly continue.
Thank you, Amino. My name is Bushra Jabin and I'm from
Canada. Should I stop
my
screen? Should I stop sharing my screen and you share yours, or?
Can you please continue sharing your screen?
Okay.
Okay, thank you so much. So I'm going to discuss the experiments and the results. So in the experiments, the StreamDiffusion pipeline was implemented upon the LSM, LSM LoRa, and SE Turbo, and the pipeline is comparable with the consumer GPU. It was tested on the NVIDIA RTX 4090 GPU, Intel Core i9-3900K CPU, Ubuntu 22.04.3 LTS, and NVIDIA RTX 3060 GPU. And the Intel Core i7-1270. So this was the comparability of the devices that was used. So first come the qualitative experiment evaluation of the denoising batch. So when implementing a denoising batch strategy, we observe a significant improvement in the processing time. As you can see from the graph that when applying the denoising batch strategy, there was a reduction by half when compared to the conventional unit. And the denoising batch strategy shows a significant improvement in the processing time, achieving a 2 times reduction compared to the unit loop when utilizing TensorRT. The speed up is even more substantial. StreamDiffusion outperforms the Oro pipeline, demonstrating a minimum speed up of 13 times with the TensorRT and 29.7 times without when running one denoising step. So the comparison extends to the different denoising steps, showing the proposed StreamDiffusion approach, particularly with the self-negative and one-time negative RCFG, which is the recursive cross-filter grouping. So the significantly improves the efficiency as the number of the denoising steps increases. Next comes the energy consumption. So in the evaluation of the energy consumption with a stochastic similarity filter, which is SSF, applied to the input videos with a threshold set at 0.98. The SSF notably reduces the GPU utilization in scenarios with the static or highly similar input images. In a 2 denoise step image-to-image experiments on the RDX 3060 GPUs, the average power consumption decreases significantly from 85.96 watt to 35.91, which is a lot of difference. Similarly, using one RDX 4090 GPU with the same static same input video, the power consumption is reduced from 238.68 watt to 119.77 watt. So next comes are the ablation study results. As you can see from the ablation study results on the next slide, please. The results indicate the ablation study results. The results indicate the StreamDiffusion achieves efficient inference times for the image-to-image and text-to-image generation. Yeah, as you can see from the results that notably at 10.98 millisecond for the 1 denoising step and 9.42 millisecond for the 4 denoising. 10.98 and 9.42 millisecond for the 1 denoising step and 26.93 and 26.30 for the 4 denoising steps respectively. Removal of the stream, but if we remove the stream batch processing, TensorRT, pre-computation, and input-output queue leads to increased time cost, emphasizing their importance in optimizing parallelization and processing. And as you can see, the StreamDiffusion outperforms the Oro pipeline image-to-image, especially without any optimization. And further, the SSF and self-negative RCFG, if we talk about that, performing the lightweight operations, they have not that much effect on the inference time, but they do have a little effect on the inference time, highlights the efficiency of the proposed pipeline. Next comes the qualitative results. In the qualitative results, the StreamDiffusion pipeline introduces a real-time diffusion pipeline for the interactive image generation, crucial for the applications like Metaverse and video game graphics rendering, achieving high throughput and low latency. The stream batch strategy, it restructures sequential denoising into the batched process, improving processing efficiency and reducing the need for the multiple unit inferences. And then comes the RCFG, which is the Residual Classifier-Free Guidance. It reduces the computational cost by minimizing the negative conditional denoising steps, leading to the significant speedups compared to the traditional methods. That's why it had a good effect on the inference time. Then comes the input-output queue. It manages the disparity in the sequence between the data input and model throughput, parallelizing the streaming process, enhancing overall system speed. Then comes the stochastic similarity filtering. It reduces the GPU activation frequency and improving the GPU utilization efficiency. And the last one is the model acceleration and the tiny autoencoder. It employs the TensorRT to construct the UNet and VAE engines, further accelerating the inference speed. So we can see that the StreamDiffusion pipeline demonstrates a real-time image-to-image transformation capabilities, producing high-quality images aligned with the specified prompts for applications such as game graphics, camera filtering, face conversion, and AI-assisted drawings. RCFG improves the image alignment compared to the models without guidance, allowing modifications like changing their hair color and adding patterns. The self-negative RCFG enhances prompt effectiveness but may increase image contrast mitigated by the adjusted parameters. One-time negative RCFG with suitable prompts balances contrast and promote adherence. The text-to-image generation using the ST-Turbo models achieve high-quality results at a rate exceeding 100 frames per second, with the potential to continuously produces 150 images per second with increased batch size. LCM LoRa models offer flexibility but may reduce speed for the diverse expression generations. So next come the what we learned, and for that I would like to invite Asta for that. So thank you.
Yeah, Esther, we cannot hear you. Esther, we can't hear you.
Let me check on my headsets. You can hear me now, right?
Yeah, we can hear you. We can hear you.
Apology for that. So on my end, what I'll kind of summarize what we've learned. For the whole paper, I'll look at the limitations. I will look at the potential applications, the future directions for research. Then I'll finalize on pros and cons. So on the limitations, next slide, kindly. On the limitations, when we talk of stream diffusion, we generally talk about the pipeline and the models. So when we talk about the limitations in terms of energy consumption, when we look at the stream diffusion in terms of pipeline, its pipeline is efficient and energy saving, but now maintaining the diffusion models in an intensive mode, now it can be energy consuming because it continuously uses the GPU. Another limitation, we found that it has a negative conditional denoising, as we had previously seen some graphs. Traditional implementation of classifier-free guidance are inefficient due to redundant computationals in negative conditional denoising. So we saw that although the proposed RCFG reduces the number of negative conditional denoising steps, there are still some computational costs that are associated with these processes. So those are the limitations. Next slide, kindly. Another limitations we have on our end was additional computational for RCFG. We saw that one of us was representing RCFG and CFG. On RCFG, we had additional steps. We were looking at them to make sure that the images were finer and they looked real. We had some additional steps for self-negative and one-time negative. So literally, RCFG comes with the additional computational. That is, it involves self-negative and one-time negative. But as CFG, we had no self-negative and one-time negative. On another limitation was impact on inference time. we all know that when we do, the number of denoising steps increases, the difference in, as the number of denoising steps increases, the difference in inference time between the conventional CFG and RCFG becomes more pronounced. Like literally it will affect potential overall speed. The latency might be so high. So like running one time before you move to the next step, it takes a lot of time. So that is the limitations we found on our end. So those are the 4 limitations we highlighted. The potential application of stream diffusion, it is so diverse. So we highlighted some of the potential applications. The applications, one of them was in Metaverse, whereby stream diffusion can be utilized in the Metaverse for real-time image generation, enabling interactive experiences with high throughput and low latency. Another potential application is in video game graphics rendering, where by the pipeline's efficiency in generation images in real time can benefit video game graphics rendering, enhancing the visual quality and responsiveness of games, making sure that the quality is high. Another potential application is live video streaming and broadcasting, whereby now we take stream diffusion in terms of improving the efficiency of live video streaming and broadcasting. We make sure that high quality images and videos are produced. That is the potential application. Another application in virtual YouTubers, whereby applications involving virtual personalities like virtual YouTubers can leverage stream diffusion to create responsive and interactive digital personas that react fluidly to user input. Another application we can look at is in online content creation, where content creators can make use of this stream diffusion now for AI assisted drawing, applying the real-time cameras, filters, and rendering 2D illustrations from 3D avatars, enhancing the creativity and efficiency of content production. So this will benefit a lot the content creators. And then we have another application is AI applications. So we saw that the pipelines has the ability to generate images from text or images prompts, which can be beneficial in various AI applications. So it can be text to image generation, image editing, and video generation. Another application we can use stream diffusion is in cross-domain image generation, whereby stream diffusion can be extended to support cross-domain image generation, whereby it will allow the creation of diverse content across different domains like portraits or cityscapes. Another application you can look at is in real-time data augmentation, whereby researchers and developers can use stream diffusion for real-time data augmentation, generating new data points based on existing data to enhance training processes for other AI models. There is second last application is in multi-user interactive platforms, whereby the pipeline's real-time interactive capabilities make it suitable for multi-user interactive platforms, whereby the multiple users can engage simultaneously in generating images or content. Like we don't have to say that we need one person to manage the platform. Like we can have several multi-users at the same time. So that is the advantage of stream diffusion. The last potential application we have is in VR application, that is virtual reality, whereby stream diffusion's high throughput and real-time images generation make it valuable for VR applications, where immersive and responsive visuals are crucial for user experience enhancement. So those are the potential applications we highlighted now in stream diffusion, whereby we know we have the limitations, but when we have these applications in place, there are some 2-3 areas we can improve and make sure that these machine learning and this AI app is helping in the industry. So the future directions for research, we have on our end now, we were thinking of now advanced CFG. Further research can be conducted to develop more efficient and accurate CFG methods that can reduce computational costs and improve image quality. Because at the end of the day, each and every app that we develop, each and everything we need, it will have to make sure that we have to put in consideration the issue of cost. So like we need to have a quality app, but at the end of the day, it is reducing cost. Another future directions for research is energy efficient strategies, whereby we need to investigate new strategies to reduce energy consumption during the interactive generational process. This could involve optimizing GPU utilization, reducing GPU activation frequency, or developing more energy efficient diffusion models. Like we need now maybe to look at, can we rule out the issue of GPU now that GPU needs a lot of space? Can we come out with something that reduces this? Another future directions for this research is on real-time interactive applications, where we need to explore real-time interactive applications that can benefit from the StreamDiffusion pipeline, such as the VR, virtual reality that we are talking of, gaming or live video streaming. The next future directions for research we were thinking of is in next slide, kindly. Multi-device integration, whereby now we need to investigate how to interact the StreamDiffusion pipeline with various devices. Can we do this in smartphones? Can we do this in tablets? Can we do this in laptops? So that it's not just cameras, it's not just specific cameras. Can we make sure that maybe someone who have just an iPhone or Android can do this? Another future directions for this research is multimodal generation, whereby now we need to research how to extend the StreamDiffusion pipeline to support multimodal generation, allowing for the generation of images, videos, or other media types. Then adaptive diffusion modeling, where now we need to develop adaptive diffusion models that can adjust their parameters based on the input data, improving the generational quality and efficiency. So all these future directions, majorly we need at least to make sure that we are inputting other devices, that someone not just in AI department or where we are reducing cost, yes, but now we need to make sure that it is accessible to everyone. Someone who have an Android, someone who have a tablet, someone who have an iPhone, can we use this streamlined diffusion for our benefit? Next slide. Next slide, kindly. Multi-device integration. This one, I'm done with that. So on our conclusion, we highlighted the pros and cons of stream diffusion, whereby on pros we were looking at the efficiency improvement. The stream batch strategy enhances efficiency by transforming sequential denoising into batch processing, leading to 1.5 times speed up compared to traditional methods. We are in a generation whereby people value their time. So we need to make sure that now we are having 1.5 times speed up compared to traditional methods. That is a plus, because we are in era of technology where time matters, speed matters. So the cons is in dataset information, whereby the paper does not explicitly mention the dataset used for experiments. So these can limit the reproductivity and comparison of results with other studies, because people need to see the data. Another pros, reduced computational cost. The residual classifier, that is RCFG algorithm, reduces computational cost by approximating negative conditional with virtual residual noise, achieving up to 2.05 times speed ups compared to conventional methods. The cons here now, we look at the proposed methodologies like RCFG, an input-output queues strategy may introduce additional complexity to the diffusion pipeline, potentially requiring more computational resources or expertise for implementation, which is the fact, because when you need quality, you need to input the cost. It comes with the cost. Quality comes with the cost incurred. Another pros we have is energy consumption optimization, whereby the paper introduces a stochastic similarity filtering strategy that significantly reduces GPU power usage. That is a plus on our end, improving energy efficiency by 2.39 times on one RTX 3060 GPU and 1.99 times on one RTX 4090 GPU for static scene inputs. The cons is a dependency on GPU. Now, while the strategy to improve the GPU utilization efficiency, the reliance on GPU acceleration may limit accessibility for users without high-end GPUs. So this one will really limit people. Like maybe you have a tablet, you need to use the StreamDiffusion, so it will limit you literally. So that is the cons. That is what I have on my end. We have the collab links for StreamDiffusion and the link to the paper. Thank you. If you have any question.
Thank you very much for that, Bushra and Esther. Thank you very much.